Right, thank you. So I'm Peter Sammonds. I'm from UCL Institute for Risk and Disaster Reduction. I'm going to talk about our project on sea ice dynamics, the role of broken ice in multi-scale deformation. Just acknowledge co-authors and others. So Sally Scorfield, a PhD student, very much the subject of her PhD, which she's now past subject to revisions. Ben Lishman from South Bank University, Mark Shaw, a PhD student of mine, Eleanor Bailey from CCOR, Alexei Marchenko from UNIS. This was funded by Hydrolab, Total, and Sam's Clock. And of course, thanks very much to the HSVA Ice Basin crew. Just say something about the Institute for Risk and Disaster Reduction. These are obviously not like a traditional civil engineering department, but we do deal with risk. We do things like publish this disaster scenario outcomes of looking at Arctic risks, which is trying to inform policymakers as well as just scientists. Our annual report, that's our old one. Our new one will be out shortly for 2019. And this is obviously looking at the fires in multi-story buildings. And just say, as well as research, we do masters teaching as well. So quite a big masters program in risk, disaster, and resilience. So just an introduction where I come from. And just say something this is slightly small. We're not really going to talk about this particularly, about where we've been coming from for pretty much the last 10 years, and that's to look at rock mechanics, look at earthquake mechanics, and use the rate and state friction laws and apply these to sea ice dynamics. And the reason why we prefer the rate and state friction laws rather than sort of simple Hamilton or Coulomb law is actually in the rate and state friction laws you can introduce a state variable. So that's to say how the ice has been over time, or how the ice has been over temperature, and so you're not sort of lumping everything together into this coefficient of friction parameter. So we published this first of all in 2011 in Journal of Geophysical Research. And also we're interested in the micromechanics as well. A number of people here contributed to the Royal Society volume we had out at the end of 2016, looking at the microdynamics of ice and trying to look at the microphysical explanations of even very large-scale mechanical behaviour. So, what is a problem we're trying to pose? So, I think one problem we're really trying to pose is something again that really struck me a long time ago now, but sort of made me think about these things, was a wrong box radar sat imagery of the Arctic basin and showing the sea ice cover as these shear lineaments, and the idea that actually the dynamics of the Arctic ice pack is very much by large scale shear on these very long lineaments. So you might have leads opened up by tensile fracture, but then you have shear on the leads. And the idea, that so sort of a conceptual model for Arctic ocean dynamics is mostly controlled by tensional fracture and frictional stick slip. Obviously, fracture compression is important for ridging and local contact. I think sort of the question we've been trying to pose is, what is the right law for sea ice friction? Is ice rupture dependent on the slip displacement? So how much the sliding goes on. Is there a characteristic length scale associated with sea ice dynamics? Can we apply fracture mechanics? And this, I think, we need experiments to investigate this. And so, if you just crank the time back a little while ago to, I think it's 2010, it might be slightly earlier. Anyway, I'll put in 2010, that's what I said when I was writing this. So our early experiments at the HSVA in the environmental ice tank, where we were doing these frictional sliding experiments where we were using the ice bridge to push central slab of ice between two outlying slabs of ice. So this is providing the force, and then we've got these pusher plates on the side providing the normal load. And we heavily instrument this just as we would an experiment, in a small-scale lab experiment. So like measuring the slip displacement with sensitometers. We have these mercury rosettes, which obviously we have difficult to transport these days. But anyway, frozen into the ice, BP sort of stress sensor, so we can measure the local stresses. Measuring local strain gauge rosettes, measuring the acoustic emissions. So these highly instrumented experiments. And just on the far corner is two mathematicians showing they're not just mathematicians as well. Helping us cut up the ice, I think, as Andre mentioned. It's a lot of very physical work to produce these sorts of experiments. And then there's sort of, conceptually what we're doing. Somebody in rock mechanics would say, view this simply as a double direct shear friction experiment. So it's really quite a simple sort of experiment in many ways. But, this sort of just showing that sort of experiment setup, again showing the stress rosettes, displacement transducers, the load cells, the load pusher plates, transducers labeled there. I mean, sort of 22 experimental runs that produce 100 million data points. So that these experiments generate a very large volume of data. And you actually can't see this very well, but this shows the experiment showing the shear stress against slip displacement. And you can see this irregular stick-slip cycling of the load. So predominantly we found stick-slip behavior, frictional behavior. We then moved our focus to the Arctic. So we then had two field campaigns supported by UNIS. And what we were doing then at this point was say, okay, so we've done these quite simple experiments, but actually we need to think about what happens when rock mechanics or earthquake mechanics will say got a full gouge between the sliding surfaces. And so that became the focus, and particularly very much with Sally Schoolfield's PhD specifically to look at the role of broken ice. So we had two field campaigns in one in the Barents Sea, one just in the Svea field, which many of you also know. But the disadvantage with this sort of experiment is, even though you've got all the parameters in there, ocean current, salt, all the rest, the controls are not as good as in the lab. And so I think one quite significant result to come out of this is published in our COAC proceedings. Ellen Shilson's already put a slide on this quite a lot. The idea, if you look at load against hold time in a friction experiment, you seem to have these two quite different regimes. You have one regime at lower hold times where you have friction control, and at high hold times you go to consolidation control. And so it depends very much which regime you're in, which sort of loads you're going to experience. So that comes on to our experiments in 2017. Again, going back now to the large ice tank at HSVA. It's actually low salinity, so there's some comparison issue there on high salinity. But again, this sort of shows the experimental setup. Again, double direct shear experiment, but now we have a rubble in between the ice blocks which are pushing in on the side and the ones that are pushing along there. So, and we created the rubble 4 different sorts of rubble, circular discs of 2 sizes, and angular sort of rhomboids of 2 different sizes as well, to have angularity and roundness. We also sort of updated the instrumentation a bit, sort of using these laser reflectors to measure displacement as well, and other things. But a sort of experiment that we were doing before, but this time actually with this broken ice acting as a full gouge. So this is a sort of experimental result. We just say that we observe with the gouge, with the broken ice, we observe both stable sliding and stick slip friction, and this is plotted now as the coefficient of friction simply taken as a ratio of the applied force, the normal force, going up to the peak, getting what we call breakdown stress drop, and then we have sliding. This shows some of the acoustic emissions that we were gathering at the time. So we clearly have a rush of acoustic emissions. So this acoustic emission amplitude here plotted against time, quite high amplitude events actually when we have the breakdown stress drop. But also, I mean, there's clearly some fracturing going on before that in the stable sliding regime, when we have a lower amplitude acoustic emissions. And again, I mean, we will present at IUTAM in a couple of weeks' time in far more detail about this, but again, we sort of see the same sort of behavior of a transition between friction-controlled and consolidation-controlled behavior as we plot coefficient of friction this time against hold time. So just to sort of summarize what we did, our experiments, displacements, deformation of broken ice were characterized through ongoing frictional slip for the first time. We observed both stable sliding and stick slip behavior. By measuring the local stress, local strain, acoustic emission, we believe that we have captured the slip mechanics. By measuring the friction under conditions of both step velocities and step hold times, we can incorporate the broken ice gouge into a modified breaking state friction law. And this will be developed full analysis of our experimental results, which say as a subject of Sally's PhD thesis. Again, we see the same thing. If effective peak coefficient of friction falls into 2 distinct regimes, a low coefficient of friction regime and a high coefficient of friction regime. And the first regime is controlled primarily through the Rabel dynamics, and the second regime is controlled primarily by consolidation. So, thank you. Thank you.
Thank you. So we have time for a few short questions.
And one blocks were compared over a long time, but probably temperature changed as well. Then with temperature here.
Yeah, I mean, we couldn't control temperature in the ice tank, but that's when we go back to the small-scale temperature experiments in the laboratory, where we do have a control on temperature, and we have done different temperature regimes to look at that. I hear what you're saying, that actually the temperature itself, work is being done, and temperature would work. Yeah. No, I think that's right. There's a temperature control, but I mean, often temperature and time, certainly what mechanics are seen as like Tweedledee and Tweedledum, 2 sides of the same coin in some ways.
One more question, but if it would be in fresh and saline ice, do you think that the time scale would be different or the same?
In freshwater ice. So, okay, so I mean, So I mean, in now back in our ice physics lab, I mean, we have done freshwater low salinity and high salinity. I mean, when I say high salinity, I mean ocean salinity experiments. I mean, the salinity has a strong effect on the consolidation process. And we published that with Eleanor Bailey